Hi class, welcome back to thermodynamics. In this lecture, we are going to go through a couple different applications of the Rankine cycle for vapor power systems. So as you recall, last lecture, we learned about isentropic efficiency and the Rankine cycle. So let's just jump right into a problem from the text since these are quite involved at this point. And the really cool thing is that we're putting together all these pieces that we've learned throughout the semester. And now we're applying all those little parts to one problem. So it's like a really big puzzle at this point. Now, this is number 22 from chapter 8 in your book. Superheated steam at 8 megapascals and 480 degrees Celsius leaves the steam generator of a vapor power plant. Heat transfer and frictional effects in the line connecting the steam generator and the turbine reduce the pressure and temperature at the turbine inlet to 7.6 megapascals and 440 degrees Celsius, respectively. The pressure at the exit of the turbine is 10 kilopascals, and the turbine operates adiabatically. Liquid leaves the condenser at 8 kilopascals and 36 degrees Celsius. The pressure is increased to 8.6 megapascals across the pump. The turbine and pump isentropic efficiencies are 88%. The mass flow rate of steam is 79.53 kilograms per second. So then there are several things we have to determine. The net power input in kilowatts, the thermal efficiency, the rate of heat transfer from the line connecting the steam generator and the turbine, the mass flow rate of the condenser cooling water in kilograms per second if the cooling water enters at 15 degrees Celsius and exits at 35 degrees Celsius with negligible pressure changes. So first things first, we need to just set up a visual of this problem. So I'm going to update this generic diagram we have here of a power plant of the Rankine cycle. And I put my little dots over for consistency so that we're dealing in rates. So in power, kilojoules per second or kilowatts. And now this is, take it one step by step and make sure you know what the problem is saying. So in this problem, this boiler is going to be the generator. Okay. So superheated steam, okay, so no liquid present, superheated steam at 8 megapascals and 480 degrees C leaves the steam generator. So right at the exit of the generator, right here, we're going to have pressure P1, and I'm going to call this P1G because it's right out of the generator. It's going to be 8 megapascals, and I'm going to call this T1G, and that is 480 degrees Celsius. So in this line, think of an extended line from the generator to the turbine. So it's following a longer path here. And because of friction, we're actually losing heat. And so when we enter the turbine here, I'm going to call this P1T, the pressure going into the turbine is reduced to 7.6 megapascals and 440 degrees Celsius. Okay, so next piece of our problem is that the pressure at the exit of the turbine is 10 kilopascals. So P2 is 10 kilopascals. And the turbine operates adiabatically. So this Q12 is 0. liquid leaves the condenser at 8 kilopascals and 36 degrees Celsius. So leaving the condenser, we have a liquid. So we're at the liquid phase, and P3 is 8 kilopascals, and T3 is 36 degrees Celsius. So the pressure then is increased by the pump, so power is going in to operate the pump, and it's increased to 8.6 megapascals. So P4 is 8.6 megapascals. And so just a pump should not, unless we're losing heat or something, the pump should not change temperature. So T4 is 36 degrees Celsius. All right, and we know that the isentropic efficiency of the turbine, so eta T, is going to be 0.88, and eta P for the pump is also going to be 0.88. We know the mass flow for this problem, m dot, is equal to 79.53 kilograms per second. And so what we're trying to find now is the net power input. So that's W dot cycle, the net input, and B, the thermal efficiency. So that is just regular eta. The rate, C, is the rate of heat transfer from the line connecting the steam generator and the turbine. So that's Q dot, and I'm just going to call it 1. So that is for the process. So that is from G. So this 1G. So when it exits the generator, it's the heat lost where it enters the turbine. Okay, so that's between 1G and 1T. So it's technically still a process. And then finally, we want the mass flow rate of condensing cooling water in kilograms per second. If the cooling water enters at 15 degrees C, so let's call this 5, and we'll call this 6. Okay, so T5 is 15 degrees C. And T6 is 35 degrees C, and there's no pressure changes. And we're looking for m dot then of the cooling water. So m dot CW, which might not necessarily be the same as m dot since they're different lines. Okay, so we have set up our givens, and now let's go through the solution. And really, the best way to approach one of these big systems problems, these cycle problems, is to go and try to determine the enthalpy and entropy for each state. So for 1, 2, 3, 4, and onward. All right, so let's go step by step. We're going to be using the property tables a lot here. And this setup part is going to take some time, and then the actual calculations after we have set up each state should be pretty quick. So let's get to it. And feel free to pause it here and try to figure out the enthalpy and entropy for each state on your own first. Okay. So this is, well, let's move this back. .22. Okay, so solution. Let's get right solution up here. So let's begin with state 1G. So right when we get out of the generator, we know that our pressure is 8 megapascals. We know that our temperature is 480 degrees C. And we know that we're superheated. So if we go and we look at table A4 in our textbook, which is for superheated vapor, we can just go ahead and look up that the enthalpy is 3,348.4 kilojoules per kilogram, and that the entropy here is going to be 6.6586 kilojoules per kilogram Kelvin. All right, so one down, many more to go. So let's look at the turbine. So 1T. So right before we get into the turbine, we're down to 7.6 megapascals for pressure. For temperature, we're down to 440 degrees Celsius. And I'm just going to pause it for a sec so I can pull up my electronic table so you can see it too. And we're back. So looking at the properties of superheated water, so we're at a pressure of 7.6 megapascals, which is going to be super fun with these tables because we're given a table for 6 megapascals and 8. So we're going to have to interpolate, and we're looking at 440 degrees Celsius. And let's start by looking for enthalpy. And another thing to notice, so right here, 440s in this row, if you go down to 8 or move up to 8 megapascals, 440s in the middle here, okay? So that could be just a little trickier than it needs to be. So what we're going to do is we're going to start at our lower limit for enthalpy at a pressure of 6 megapascals. So we're going to take the 3,277.3 kilojoules per kilogram. Then we're going to add to it the difference between the pressure we're at, which is 7.6 megapascals, our lower limit here, which is 6 megapascals, and then we're going to divide that by the increment in the table. So 8 megapascals minus 6, so 2 megapascals. And then we're going to multiply that by the difference between the upper and lower limit here. So the difference between at our higher pressure, we're at 3,246.1 kilojoules per kilogram, and we're going to subtract from that 3,277.3 kilojoules per kilogram. And also notice that when we increase pressure for the same temperature, we reduce enthalpy. All right, so you should have a negative number in there, so you should be at something, we will ultimately end up at something slightly lower than 3,277.3. Okay, let's give it a try. So I'm just going to write this all in. We just talked about it. So H1T is going to be 3,277.3 plus 7.6 megapascals minus 6 divided by 8 megapascals minus 6 times 3246.1 minus 3277.3, and this is all in kilojoules per kilogram ultimately. And so H1T is going to be, let's see, 3,252.3 kilojoules per kilogram. Okay, now we get to do the exact same thing for entropy. So following the same pattern here. So the lower limit for 6 megapascals of entropy at 440 degrees Celsius is 6.6853, and then it's going to be the same ratio here, the 7.6 minus 6 over 8 minus 6, and then the upper limit entropy, so for the higher pressure, it's going to be a lower entropy, so that's 6.6853 0.5190. And that makes sense, right? There's going to be, if there's more pressure at the same temperature, then there's going to be fewer configurations, so less disorder, slightly lower entropy. And we're going to subtract off 6.6853, and we're in kilojoules per kilogram Kelvin. And so for entropy, we end up with 6.5526 kilojoules per kilogram Kelvin. Okay, done with state 1. So now let's move on to state 2. So this is where we exit the turbine. So let's add a page for this. So when we exit the turbine, some things we know. We know that our pressure is 10 kilopascals. And so another thing we know about the turbine is that the efficiency of the turbine, the isentropic efficiency, is going to be 0.88, which is going to be WT over WTS. So this is on a mass flow basis. So these are lowercase, which is going to be H1T minus H2 divided by H1T minus H2S. So remember the S's here denote isentropic. So this would be the isentropic entropy at the isentropic enthalpy at the outlet. And so the thing is here, we know what the isentropic enthalpy is because what that means is between state 1 when we enter the turbine and state 2 where we exit the turbine, we're not getting any change in entropy. So delta S is 0. So we know that S1T is equal to S2S, which was 6.5526 kilojoules per kilogram Kelvin. So let's go to our tables then and see if we can figure out what temperature we're at, what H2S is. And from H2S, we can go ahead and solve, once we know H2S, we can rearrange and solve for H2. But let's just start by getting our H2S first. So I'm going to open up the tables, and we're at a pressure of 10 kilopascals. So I'm going to move, so I have a feeling we're going to be in the liquid vapor tables, and we have to look at it with pressure in the first column. And so 10 kilopascals is 0.1 bar, just divide by 100. And we're looking for our entropy is 6.5526 kilojoules per kilogram Kelvin. So we're somewhere in here. So yes, this is the proper table, and that means we're definitely at a temperature of 45.81 degrees Celsius. So our temperature, so we know that T2 is going to be 45.81 degrees Celsius. So now that we know what our entropy is, we know which table we're in, we can go ahead and we can figure out what the quality of this ideal process, of this isentropic process would be. And in order to determine the quality, it's going to be the ratio between the entropy you're at, 6.5526, minus the lower limit where the quality is 0. So in this case, that would be 0.6493. And then we're going to divide by the entire range. Okay, so minus 0.64 And we're going to divide by the difference between 8.1502 and 0.6493. And this is going to give us an isentropic quality of 0.787. Okay, we're getting there. So now that we know the isentropic quality, we can go ahead and we can apply that to figuring out the isentropic enthalpy. So H2S then is going to equal 1 minus 0.787, which is going to be, let's see, 0.213. Times our saturated liquid enthalpy, which was in our tables 191.83, plus the proportion vapor, so 0.787, times the saturated vapor enthalpy, which was 2,584.7. And all this is going to be in kilojoules per kilogram. And so H2S is going to be 2,075 kilojoules per kilogram. Okay, so now we can go ahead and we can solve for H2. H2 is going to equal H1T minus eta T times H1T minus H2S. So I'm just rearranging this equation up here. And so now we have all our pieces we can plug in. And so H1T was 3,252.3, and eta is 0.88. Okay, plug in H1T again, and subtract off H2S, which we just found, 2,075, and this is going to be in kilojoules per kilogram. And so H2 is going to be 2,216.3 kilojoules per kilogram. And you would think we would be done for state 2. Not quite yet. So remember, now we have to find that entropy for state 2, because this was not an isentropic process. We're just looking at the ideal to figure out what is really going on. So now we have to get our quality, our actual quality for state 2, our real quality. So let's keep going. So our real quality for 2, so we're still on state 2 here, is going to be the difference between the enthalpy that we have, which we just calculated for H2, which was 2,216.3, minus our lower limit on enthalpy here. So remember, we're at 10 kilopascals. Our lower limit on enthalpy is 191.83, so that's when we're at a saturated liquid. So minus 191. And then I want to show you something cool. So we could just subtract off the bounds, right? The upper saturated vapor enthalpy minus the saturated liquid enthalpy. So the table does that for us. That's what this HFG is. So the difference between the two is 2,392.8. So instead of subtracting 191.83 from 2,584.7, we can just skip that step and write in 2,392.8. So I'm going to write that into my denominator. And we get a quality of 0.8461. Okay, So now we can calculate our entropy. So our entropy is going to be 1 minus 0.8461, which is going to be 0.1539 times 0.6493. Okay, so that's the liquid enthalpy, the saturated liquid, plus 8.461 times the saturated vapor enthalpy, which is 8. Oops. Undo that. Undo one more. Okay, so 0.8461 times the enthalpy, which is the entropy. It's so hard to say those. 1502. And this is kilojoules per kilogram Kelvin. And so this is going to give us S2 is equal to 6.9958 kilojoules per kilogram Kelvin. Now, for state 3, okay, we know that we're at a pressure of 8 kilopascals. And our temperature is still 36. Sorry, I was looking at the wrong line. T3 is 36 degrees Celsius. Okay, so here we are dealing with a liquid. We're told we're dealing with a liquid, and so we can approximate H3 at our saturation temperature from the table. So at 36 degrees Celsius, we're just going to look at H sub F from the table for saturated liquid is how we can approximate the enthalpy for a liquid at any temperature. And this is going to give us 150.86 kilojoules per kilogram. And we don't need to worry about the entropy here, especially because moving through the pump from state 3 to state 4, so for process 3-4, we're not changing temperature, and so the entropy is not going to change. Well, all right, well, because we're changing pressure, we are changing entropy, but it's not anything that we're going to need in our analysis. So strike that, never said that. Okay, and so let's move on to state 4. And I'm just realizing I can draw on my picture here, which is kind of fun. All right, so 4, we're increasing the pressure with our pump to 8.6 megapascals. And the temperature is going to stay the same. So now we can get the isentropic enthalpy can be approximated by the following. And this is from an equation in your textbook. And I have posted a handout with all kinds of hints and equations for isentropic processes, for isentropic efficiencies, for the Rankine cycle. For next lecture, we're going to be looking at the Carnot cycle for vapor compression refrigeration systems. So that's all in a helpful handout that you can, of course, use on any exam, any quizzes to help with your homework, to look on at while you're going through these lectures. So that is a useful tool. Okay, so that's going to be equal to the enthalpy going in to our pump plus, so the specific volume times P4 minus P3 is how we get the isentropic enthalpy at the outlet of a pump. In this case, we can look up our specific volume. So V3, what we're doing is we're just looking at our liquid vapor tables for water at a temperature of 36 degrees Celsius and looking at V3, which would be VF, so for 100% liquid, so quality of 0, and that it gives us 1.0063 times 10 to the minus 3 meters cubed per kilogram. Okay, so H4S is going to be our H3, which is 150.86 plus 1.0063 times 10 to the minus 3 times 8,600. Okay, because we're dealing with 8.6 megapascals, which is 8,600 kilopascals, minus 8 kilopascals. So our metric prefix in this case is consistently kilo. And so we'll end up with kilojoules per kilogram at the end. And I'm going to open up a new sheet to put our H4S. All right. And so we're still on 4. H4S is going to be 159.51 kilojoules per kilogram. And we're also, remember, given our isentropic efficiency for the pump, which was also 0.88, which is going to be equal to the isentropic work input over the actual work put into the pump. And so it's going to be H4S minus H3 divided by H4 minus H3. And so we can rearrange and solve for H4, which is going to be H3 plus H4S minus H3 divided by eta P. And now just plugging in, we're going to get that H4 is equal to 150.86 plus H4S was 159.51 minus 150.86 divided by 0.88. And this is kilojoules per kilogram. And we end up with H4 is equal to 160.69 kilojoules per kilogram. Okay, almost there. So now let's actually just get some satisfaction from this and go ahead and just start answering the different parts of the problem now that we set out to answer and find. So it's all worth it, right? Delayed gratification here. All right, so for A, we're looking for W dot cycle, which is going to be equal to M dot times WT minus WP. And so just note, these are lowercase, so they're on a mass basis. So the units in here would be kilojoules per kilogram, whereas the mass is mass flow rate, which is kilograms per second. And so that will ultimately give us kilowatts or kilojoules per second. Okay. And so W dot cycle is equal to M dot, then WT can be found from H1 minus H2, and WP is H4 minus H3. And for this, we're dealing with what's actually going into the turbine, so H1T. Okay, and now we just plug in. So M dot was given to us, and that's 79.53 kilograms per second times 3252.3 minus 2216.3 minus 160.69 minus 150.86, and these are kilojoules per kilogram. And so we end up with W dot cycle is equal to 81,610 kilowatts. So it took a lot of work to get there, but we made it. So there's part A. So part B, we're looking for eta, so the cycle efficiency, and that is going to be equal to W dot cycle divided by Q dot in. So this is going to be then, in other words, W dot cycle divided by M dot H1G minus H4. Okay, so we look at H1G here because we have some friction losses and we're trying to figure out what the total heat going in was. So you have to think about that as well. And so we end up then, so that's with, and of course the Q in is the generator. See, that's where you have the Qn. So 4 to 1, and that's the 1G. Okay, and so this is going to be equal to 79. Oh, just kidding. It's in the denominator. 81,610 kilowatts divided by 79.53 kilograms per second, and a kilowatt times a second is a kilojoule. And then what we'd like to do is do H1G minus H4, which is going to be 3348.4 minus 160.69 kilojoules per kilogram. Okay, kilograms cancel, kilojoules cancel. So we end up with our efficiency, which is unitless, and 0.322 is what we get, which is the same as 32.2%. Okay, there's part B. Now, almost there. Okay, so for this, for part C, we were looking for that heat lost in that line. So that's going to be between the turbine and the generator. So that's going to be M dot times H1T minus H1G. Okay, so it's what was our losses due to friction. And so this is going to be 79.53 kilograms per second times 3252.3 minus 3348.4 kilojoules per kilogram. And this is going to give us minus 7643 kilowatts. All right, last one, we're looking for the mass flow of the cool water. And so if you were going to do an energy balance and rearrange and solve for m.cw, you end up with m dot for our main line, H2 minus H3, divided by H6 minus H5. So this would be doing a steady state energy balance, saying that 0 is equal to m dot H2 minus H3 plus m dot cool water times H6 minus H5. So what we're looking at is, let me just show you. So here we're in the condenser. So the enthalpy difference here should equal the enthalpy change here. Well, the total energy, which is dependent on m dot. So our m dot is going to be, well, we would need to look up H5 and H6. So dealing with liquid water, we're just going to use the liquid vapor saturation table. So we're just going to look up HF at 15 degrees C, which is 62.99 kilojoules per kilogram. And H6 is 35 degrees Celsius, which is going to be 146.68 kilojoules per kilogram. So m dot CW is going to be 79.53 kilograms per second times 2216.3 minus 150.86 divided by 146.68 minus 62.99, which is going to be 1963 kilograms per second. Whew, great, we did it. So I know we're running short on time, but you do have an exam that's due by the end of this week. And the Rankine cycle is fair game for the exam. And so I'd like you to think of this next problem as an exam practice problem. So I would like you to try this one on your own first. And then we'll go through it together. So, steady state operating data for a solar power plant that operates on a Rankine cycle with refrigerant 134A is provided below. Saturated vapor at 60 degrees Celsius enters the turbine. The condenser operates at a pressure of 6 bar, and the density of the refrigerant as it exits the condenser is 1,137 kilograms per meter cubed. Both the turbine and pump operate adiabatically with an isentropic efficiency of 88%. The rate of energy input to the collectors from solar radiation is 0.4 kilowatts per meter squared of collector surface area, with 50% of the solar input to the collectors absorbed by the refrigerant as it passes through the collectors. So first, sketch the power plant schematic showing the given values for each state. Second, draw the cycle on a TS diagram. Third, complete the table. So you're given some info for the states to make this quicker. So, you know, if you had an exam or something, you might see a problem that looks maybe a little like this. And so this should make your calculations go a little quicker. Perhaps. We'll see. The mass flow rate of refrigerant per kilowatt of power produced is 0.06 kilograms per second. Determine the solar collector surface area in meters squared per kilowatt of power developed by the plant. So sketch it out, try it on your own, and then resume when you're ready to see the solution. So let's begin with a schematic here. So this is A. All right, so let's start with our turbine. This is W dot T. So going in, that's 1. Coming out, that's state 2. And of course, the vapor, the gas, which is going to be so like superheated refrigerant perhaps, or at least gaseous refrigerant, is going to be heated in our solar collectors. So I'm going to draw some solar collectors here. So pretend those are solar collectors. And with a solar collector, what we're doing is we're getting heat going in. So from the energy of the sun, we're having our refrigerant go through these little tiny pipes in the solar collector. All right, and so it's going to heat up our working fluid, which is going to be passed through the turbine. And so then what we're going to do is we're sending, oops, into a condenser where we're going to get some Q out. And then we're going to a pump. So this is 3. We're going into a pump. Which is, of course, going to require some work going in. Okay, so there's the basics of our diagram there. And here's 4. So let's start filling in some of our given information. So T1, let's make that a T for temperature, not time. T1 is 60 degrees Celsius. Okay, the condenser operates at a pressure of 6 bar, so that means P2 is 6 bar. And the density of the refrigerant as it exits the condenser is 1137 kilograms per meter cubed. So as it exits the condenser, and that's density, so row 3 is 1137 kilograms per meter cubed. And just keep in mind what this looks like. Remember, specific volume is 1 over density, so that could give us some useful information there. The pump operates adiabatically. Okay, so with the pump, there's no heat exchange, and we're given the isentropic efficiency of the pump. The rate of energy input to the collectors from the solar radiation is 0.4 kilowatts per meter squared. Okay, so that's our energy input. And 50% of the solar input to the collectors is absorbed by the refrigerant as it passes through the collector. So you're going to have to think a little bit critically about what that means. And I think the condenser operates at 6 bar, and so that means that P3 is also going to be 6 bar. Going in and out of the condenser, we have the same pressure there. And the pressure is not going to change from the pump as it moves through the solar collectors. So P4 is going to equal P1. And what else do we know? Saturated vapor enters the turbine, so that means X1 is 1. And anything else that I'm missing? Okay. So another piece is that we're going to have a liquid that comes out of the condenser. So X3 is going to be 0. All right, so now what we can do is let's draw this on our PV diagram, and then we're going to evaluate the properties of each state. Okay, so let's look at this on, so this is part B on our TS diagram. All right, so we know we're dealing with the vapor dome. So let's draw the vapor dome on there. And so for one, I'm going to stick it right here. We are at a saturated vapor. So then for two, what is happening as we move through the turbine? All right, so we're going to move through the turbine and we're going to drop in temperature, but we're still in the vapor dome. And so 2 is going to be here. 3, we're at constant temperature, and our quality is going to be 0. And 4, we're up here. All right, so that's our sketch. And so now let's go ahead and evaluate our properties at each state. So 1, all we have to do is look at refrigerant 134 in our tables for saturated liquid vapor. Did I pass it? Yes, I did. Propane, ammonia. I went way past it, didn't I? Okay, 134A, that's what we're looking at, right? Okay, so let's go in the liquid vapor tables, and we're at a temperature of 60 degrees Celsius, and our quality is 1, and so we're at 275.99, and we can also get the entropy pretty easily from there, and we could also figure out the temperature we're at. We're at 16.813. I mean the pressure. We're at 16.813 bar. So let's just do P1 equals 16.813 bar. H1 is going to be 275.99 kilojoules per kilogram. S1 is going to be 0.8973 kilojoules per kilogram Kelvin. Okay, so now let's look at state 2 if we had ideal conditions. So if we were dealing with an isentropic turbine. So then for 2S, we're going to have S2S is equal to S1, which is going to be 0.8973 kilojoules per kilogram Kelvin. So we can get our quality, X2S, is going to be the difference between 0.8973 minus 0.2999 divided by 0.9097 minus 0.2999. And so this is going to give us 0.9797. So we're still really close to saturated vapor there. And so then we can go ahead and find H2S, which is just going to be 0.0203 times 79.48 plus 0.9797 times 259.19 which is going to give us 255.54 kilojoules per kilogram. All right, and then what we can do is, knowing that eta T, which we're given, is also 80.88. There we go. So eta T is 0.88. And that is going to be then equal to H1 minus H2 divided by H1 minus H2S. And so that's going to give us that H2 is eta T times H1 minus H2S minus H1. And so we get 257.99 kilojoules per kilogram. All right. And that was minus H2, and this is positive H2. Okay, and so let's move on then to state 3. So state 3 is going to be H3 is going to be 79.48 kilojoules per kilogram. And that's with the quality of 0. So just looking at pressure of 6 bar. So you can look at that in our table here. State 2S is also at 6 bar. Hint, hint. So this is the info for 6 bar. All right. And so S3, you can just look up. Which is going to be 0. Hold on 1 second. Just noticed something funky in my notes. All right, so S3 is going to be 0.2999 kilojoules per kilogram. All right, and then for state 4, WP is going to equal V3 times P4 minus P3, which is equal to H4S minus H3. So H4S is going to be equal to P4 minus P3. And then we were given the density at state 3, and remember 1 over density is specific volume, so we can rewrite this as P4 minus P3 over density at state 3 plus H3. And this will give us 1081.3 kilopascals is the difference, divided by 1,137 kilograms per meter cubed, plus 79.48 kilojoules per kilogram, which is going to give us 80.43 kilojoules per kilogram. All right. So, and then just remember that H4 is going to equal H4S minus H3 over the efficiency of the pump plus H3. And when this is all said and done, we get 80.56 kilojoules per kilogram. Okay, so now let's go ahead and fill in the rest of the parts of this problem. So filling in the table, the quality at state 1 is 1. And at 2s, we figured out already, was 0.9797. Okay, so that part's done. Okay, we drew it on a TS diagram. And now we have to find the thermal efficiency of the power plant. Okay, so for C, we need to find the thermal efficiency of the power plant. And so that's going to be eta is equal to H1 minus H2 minus H4 minus H3. And we're going to divide by H1 minus H4. And this is going to give us 0.0866 or 8.66%. Not super efficient. Okay, so for D, we have the mass flow rate of refrigerant per kilowatt of power produced is 0.06 kilogram per second. We need to determine the solar collector surface area in meters squared per kilowatt of power. Can I get back down there? Nope. Okay. So for this, we know that W cycle is going to equal m dot WT minus WP, which is going to be m dot H1 minus H2 minus H4 plus H3. And we know m dot is given to us 0.0591 kilograms per second. And so Q in is going to be equal to m dot H1 minus H4, okay, for the solar collectors. And so this comes out to 13.53 kilowatts. And what we're trying to find is the area needed for the solar collectors. So Q into the plant is half of what actually the energy that actually reached, the radiation that actually reached the collectors. Okay, so that was given to us in the problem. And so we can figure out that the energy for the collectors is going to equal double Q in, which is 27.1 kilowatts, divided by the surface area of the collectors. And so we are given that per surface area, we have 0.4 kilowatts per meter squared is the given part of our problem. So we can just go ahead and solve for A, and we end up with area is equal to 68 meters squared. Okay, well, that is it for this lecture, and I will see you next time when we get into vapor compression refrigeration systems and heat pump cycles. All right, take care.